The Big Bang theory is the prevailing cosmological model for the universe from the earliest known periods through its subsequent large-scale evolution. The model accounts for the fact that the universe expanded from a very high-density and high-temperature state, and offers a comprehensive explanation for a broad range of phenomena, including the abundance of light elements, the cosmic microwave background, large-scale structure and Hubble's law. If the known laws of physics are extrapolated beyond where they are valid, there is a singularity. Modern measurements place this moment at approximately 13.8 billion years ago, which is thus considered the age of the universe. After the initial expansion, the universe cooled sufficiently to allow the formation of subatomic particles, and later simple atoms. Giant clouds of these primordial elements later coalesced through gravity to form stars and galaxies. Since Georges Lemaitre first noted, in 1927, that an expanding universe might be traced back in time to an originating single point, scientists have built on his idea of cosmic expansion. While the scientific community was once divided between supporters of two different expanding universe theories, the Big Bang and the steady-state theory, accumulated empirical evidence provides strong support for the former. In 1929, from analysis of galactic redshifts, Edwin Hubble concluded that galaxies are drifting apart. Important observational evidence consistent with the hypothesis of an expanding universe. In 1965, the cosmic microwave background radiation was discovered, which was crucial evidence in favor of the Big Bang model, since that theory predicted the existence of background radiation throughout the universe before it was discovered. More recently, measurements of the redshifts of supernovae indicate that the expansion of the universe is accelerating, an observation attributed to dark energy's existence. The known physical laws of nature can be used to calculate the characteristics of the universe in detail back in time to an initial state of extreme density and temperature. Overview. Hubble observed that the distances to faraway galaxies were strongly correlated with their redshifts. This was interpreted to mean that all distant galaxies and clusters are receding away from our vantage point with an apparent velocity proportional to their distance. That is, the farther they are, the faster they move away from us, regardless of direction. Assuming the Copernican principle, the only remaining interpretation is that all observable regions of the universe are receding from all others. Since we know that the distance between galaxies increases today, it must mean that in the past galaxies were closer together. The continuous expansion of the universe implies that the universe was denser and hotter in the past. Large particle accelerators can replicate the conditions that prevailed after the early moments of the universe, resulting in confirmation and refinement of the details of the Big Bang model. However, these accelerators can only probe so far into high-energy regimes. Consequently, the state of the universe in the earliest instance of the Big Bang expansion is still poorly understood and an area of open investigation and indeed speculation. The first subatomic particles included protons, neutrons, and electrons. Those simple atomic nuclei formed within the first 3 minutes after the Big Bang. Thousands of years passed before the first electrically neutral atoms formed. The majority of atoms produced by the Big Bang were hydrogen, along with helium and traces of lithium. Giant clouds of these primordial elements later coalesced through gravity to form stars and galaxies, and the heavier elements were synthesized either within stars or during supernovae. The Big Bang theory offers a comprehensive explanation for a broad range of observed phenomena, including the abundance of light elements, the cosmic microwave background, large-scale structure, and Hubble's law. The framework for the Big Bang model relies on Albert Einstein's theory of general relativity and on simplifying assumptions such as homogeneity and isotropy of space. The governing equations were formulated by Alexander Friedmann, and similar solutions were worked on by Willem de Sitter. Since then, astrophysicists have incorporated observational and theoretical additions into the Big Bang model, and its parametrization as the lambda CDM model serves as the framework for current investigations of theoretical cosmology. The lambda CDM model is the standard model of Big Bang cosmology, the simplest model that provides a reasonably good account of various observations about the universe. Timeline. Singularity extrapolation of the expansion of the universe backwards in time using general relativity yields an infinite density and temperature at a finite time in the past. This singularity signals the breakdown of general relativity and thus all the laws of physics. How closely this can be extrapolated toward the singularity is debated, certainly no closer than the end of the Planck epoch. This singularity is sometimes called the Big Bang, but the term can also refer to the early hot, dense phase itself, which can be considered the birth of our universe. Based on measurements of the expansion using type Iowa supernovae and measurements of temperature fluctuations in the cosmic microwave background, the universe has an estimated age of 13.799 plus or minus 0.021 billion years. The agreement of these three independent measurements strongly supports the lambda CDM model that describes in detail the contents of the universe. Inflation and baryogenesis. The earliest phases of the Big Bang are subject to much speculation. In the most common models, the universe was filled homogeneously and isotropically with a very high energy density and huge temperatures and pressures, and was very rapidly expanding and cooling. Approximately 10-37 seconds into the expansion, a phase transition caused a cosmic inflation, during which the universe grew exponentially. After inflation stopped, the universe consisted of a quark-gluon plasma, as well as all other elementary particles. Temperatures were so high that the random motions of particles were at relativistic speeds, and particle-antiparticle pairs of all kinds were being continuously created and destroyed in collisions. At some point an unknown reaction called baryogenesis violated the conservation of baryon number, leading to a very small excess of quarks and leptons over antiquarks and antileptons, of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter in the present universe. Cooling. The universe continued to decrease in density and fall in temperature, hence the typical energy of each particle was decreasing. Symmetry-breaking phase transitions put the fundamental forces of physics and the parameters of elementary particles into their present form. After about 10-11 seconds, the picture becomes less speculative, since particle energies drop to values that can be attained in particle physics experiments. At about 10-6 seconds, quarks and gluons combine to form baryons such as protons and neutrons. The small excess of quarks over antiquarks led to a small excess of baryons over antibaryons. The temperature was now no longer high enough to create new proton-antiproton pairs, so a mass annihilation immediately followed, leaving just 1 in 10 of the original protons and neutrons, and none of their antiparticles. A similar process happened at about 1 second for electrons and positrons. After these annihilations, the remaining protons, neutrons and electrons were no longer moving relativistically and the energy density of the universe was dominated by photons. A few minutes into the expansion, when the temperature was about 1 billion Kelvin and the density was about that of air, neutrons combined with protons to form the universe's deuterium and helium nuclei in a process called Big Bang Nucleosynthesis. Most protons remained uncombined as hydrogen nuclei. As the universe cooled, the rest mass energy density of matter came to gravitationally dominate that of the photon radiation. After about 379,000 years, the electrons and nuclei combined into atoms, hence the radiation decoupled from matter and continued through space, largely unimpeded. This relic radiation is known as the cosmic microwave background radiation. The chemistry of life may have begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. Structural formation over a long period of time. The slightly denser regions of the nearly uniformly distributed matter gravitationally attracted nearby matter and thus grew even denser, forming gas clouds, stars, galaxies, and the other astronomical structures observable today. The details of this process depend on the amount and type of matter in the universe. The four possible types of matter are known as cold dark matter, warm dark matter, hot dark matter, and baryonic matter. The best measurements available show that the data is well fit by a lambda CDM model in which dark matter is assumed to be cold, and is estimated to make up about 23% of the matter energy of the universe, while baryonic matter makes up about 4.6%. In an extended model, which includes hot dark matter in the form of neutrinos, then if the physical baryon density, omega BH2, is estimated at about 0.023, and the corresponding cold dark matter density omega CH2 is about 0.11, the corresponding neutrino density omega VH2 is estimated to be less than 0.0062. Cosmic acceleration. Independent lines of evidence from type Iowa supernovae and the CMB imply that the universe today is dominated by a mysterious form of energy known as dark energy, which apparently permeates all of space. The observations suggest 73% of the total energy density of today's universe is in this form. When the universe was very young, it was likely infused with dark energy, but with less space and everything closer together, gravity predominated, and it was slowly breaking the expansion. But eventually, after numerous billion years of expansion, the growing abundance of dark energy caused the expansion of the universe to slowly begin to accelerate. Dark energy in its simplest formulation takes the form of the cosmological constant term in Einstein's field equations of general relativity, but its composition and mechanism are unknown, and more generally, the details of its equation of state and relationship with the standard model of particle physics continue to be investigated both observationally and theoretically. All of this cosmic evolution after the inflationary epoch can be rigorously described and modeled by the lambda CDM model of cosmology, which uses the independent frameworks of quantum mechanics and Einstein's general relativity. There is no well-supported model describing the action prior to 10-15 seconds or so. Apparently a new unified theory of quantum gravitation is needed to break this barrier. Understanding this earliest of eras in the history of the universe is currently one of the greatest unsolved problems in physics. Underlying assumptions. The Big Bang theory depends on two major assumptions: the universality of physical laws and the cosmological principle. The cosmological principle states that on large scales the universe is homogeneous and isotropic. These ideas were initially taken as postulates, but today there are efforts to test each of them. For example, the first assumption has been tested by observations showing that largest possible deviation of the fine structure constant over much of the age of the universe is of order 10⁻⁵. Also, general relativity has passed stringent tests on the scale of the solar system and binary stars. If the large-scale universe appears isotropic is viewed from Earth, the cosmological principle can be derived from the simpler Copernican principle, which states that there is no preferred observer or vantage point. To this end, the cosmological principle has been confirmed to a level of 10⁻⁵ via observations of the CMB. The universe has been measured to be homogeneous on the largest scales at the 10% level. Expansion of space. General relativity describes spacetime by a metric, which determines the distances that separate nearby points. The points, which can be galaxies, stars, or other objects, themselves are specified using a coordinate chart or grid that is laid down over all spacetime. The cosmological principle implies that the metric should be homogeneous and isotropic on large scales, which uniquely singles out the Friedmann-Lemaitre-Robertson-Walker metric. This metric contains a scale factor, which describes how the size of the universe changes with time. This enables a convenient choice of a coordinate system to be made, called comoving coordinates. In this coordinate system, the grid expands along with the universe, and objects that are moving only because of the expansion of the universe remain at fixed points on the grid, while their coordinate distance remains constant. The physical distance between two such comoving points expands proportionally with the scale factor of the universe. The Big Bang is not an explosion of matter moving outward to fill an empty universe. Instead, space itself expands with time everywhere and increases the physical distance between two comoving points. In other words, the Big Bang is not an explosion in space, but rather an expansion of space. Because the FLRW metric assumes a uniform distribution of mass and energy, it applies to our universe only on large scales. Local concentrations of matter such as our galaxy are gravitationally bound and as such do not experience the large-scale expansion of space. Horizons. An important feature of the Big Bang spacetime is the presence of horizons. Since the universe has a finite age, and light travels at a finite speed, there may be events in the past whose light has not had time to reach us. This places a limit or a past horizon on the most distant objects that can be observed. Conversely, because space is expanding, and more distant objects are receding ever more quickly, light emitted by us today may never catch up to very distant objects. This defines a future horizon, which limits the events in the future that we will be able to influence. The presence of either type of horizon depends on the details of the FLRW model that describes our universe. Our understanding of the universe back to very early times suggests that there is a past horizon, though in practice our view is also limited by the opacity of the universe at early times. So our view cannot extend further backward in time, though the horizon recedes in space. If the expansion of the universe continues to accelerate, there is a future horizon as well.